So this thing about efficient proofs is, in a way, this is the main point of chapter 1.
But it should be in the index or in the table of contents, efficient method or something, but it's not.
Yeah, so he just sort of demonstrates the efficient method all over chapter 1, right? It's just all over the place, but especially the big section of the book that you should look at is, the big culmination is here in section 1.14. Consistency and the science of reputation. Clearly one can program.
And that's funny because consistent is not in one of those definition boxes anywhere in the chapter, like valid is.
Right.
I think it's funny. It should be in a box.
Yeah. Well, he tries to keep it less, So he says if logic is the science of deduction, it is the science of refutation as well.
Okay.
From this point of view, formal logic aims to provide systematic means for recognizing inconsistency. Okay, so and one thing about chapter 1 for Jeffrey here is he's just kind of throwing you into the deep end and letting you hack around and be thinking, well, what is this? What is this efficient method? And then in chapter 2, we will see, now that we're aware of the problem that he's presented to us in chapter 1, is that this idea of efficiency being based in consistency is all built into the truth table method.
Mm-hmm.
So he's kind of setting us up to think, what does he mean by efficient? And what does he mean by consistent? And then the truth table, the truth trees, then show us very mechanically.
Because we start out with the negated conclusion and then show that doesn't work out.
Right. And so you've already looked at chapter 2, right?
I cheated. I peeked ahead.
Okay. So if you have an open path, that defines
a possibility,
a case where the propositions are consistent. If you have all closed paths, then your original set of propositions is inconsistent. With
that conclusion.
Well, yeah, whatever those original propositions are. It doesn't necessarily need to be an argument. You could just test a set of propositions for consistency. In essence, the truth tree is a test of consistency.
Mm-hmm.
And more than that, he doesn't just test whether it is consistent or not. If it is consistent, it gives you a model. It gives you the values, which
interpretations.
It gives you the interpretation that makes the set of propositions consistent.
Right.
So
is the efficient method then demonstrating that a counter argument either exists or doesn't exist? And
that's right.
Explaining why or why not.
That's right. Okay. But you want to cut to the chase by thinking, what would a counterexample be?
Right. Set the conclusion to false. How can you do that? There's certain.
But then you got to think about it. It depends on whether we're talking about logical equivalence or whether we're talking about an argument. And a lot of the problems, actually, he wants us to do logical equivalence. So it has to go both ways. And so your counterexample is that your left-hand side is true and your right-hand side is false, or vice versa. Your right-hand side is true and your left-hand side is false. So that's generally what a counterexample would look like. Start there. See if you get a contradiction. If you get a contradiction, then there's no counterexamples. But if you start with what a general counterexample would look like in general terms, and then get specific values for all the variables, you have a counterexample. And you can do that with logical equivalence. You can do that with an argument. You can do that even with consistency itself. Because it's all about consistency and it's all about refutation. And so that's what, this is where he kind of brings it home, is in section 1.14. And especially in this paragraph. If logic is the science of deduction, it is the science of refutation as well. And this has to do with recognizing inconsistency. And then here he has these italicized sections: how to use an inconsistency detector to test validity, how to use a validity detector to test inconsistency. So he's making the point that testing validity and testing inconsistency are logically equivalent. It's just different ways of looking, it's just different ways of looking at the same problem. And
now both of those talk about premises and conclusions, though. So 5 minutes ago, I always thought it was an argument. We had to have an argument with a conclusion that we could then negate, as opposed to just
right. That's. But I want you to think about it more generally. Okay. Yeah. And then in chapter 2, he is focusing on arguments.
Yeah.
Right. And that's I think mostly in the book we're focusing.
Because I've worked those problems like in 2 and 3.
Mm-hmm.
I didn't have any issues with those. They made sense. It was chapter 1 and where I got. That's the hard chapter. 2 and 3 were relatively easy.
So it's almost like, in a way, you don't really understand chapter 1 until you've really started to work the truth trees.
I think so.
You know, and so maybe that would be a different approach to take, is to do the truth trees. But you know.
But having 106 already, there's a lot of 1 already built in, right?
Yeah.
I knew what he was going for.
Uh-huh.
And I was just so happy that I had already had 106, because it was tough for me to read.
Mm-hmm.
And then I for sure didn't get, hey, Matt, I want you to solve a problem using an efficient method.
Yeah, right.
Okay.
And I think, you know, if I were just reading it fresh, I wouldn't see all these allusions to the sufficient method.
Yeah.
It's just when I read it, because I I'm just reading it. I'm just following the schedule and going through it again. Right.
Yeah.
And, but it's all over the place. And that's kind of, like I was saying, is kind of the main point of chapter 1, is this whole thinking efficiently.
Yeah.
So I have a bit of a lecture that I think will tie in with some of what you've done in your presentations, and it'll certainly tie in with some stuff from 106. Okay. So let me start. This is not the efficient method, but this is kind of a step in the direction of the efficient method.
Okay.
And this is very traditional. So this is normally like to prove that conjunction is associative. This is the style of proof that, like most mathematicians, they're teaching a class and, you know, we're doing like abstract algebra, and they're like associativity, you know, and like in abstract algebra, we would look at something that looks like, where is it with those section symbols?
Yeah.
You know, you'd use like some oddball symbol
Connectives.
just to represent a connective in general. I don't see where it is on here.
There.
You know, you're abstracting away from all the operations that we normally use, like addition, subtraction, multiplication. And you just say, well, an operation in general would, you know, let's just use this weird symbol here. that's just some operation. We don't really know what it does when you plug in numbers to it or plug in truth values to it. But if it's going to be associative, it has to have this structure. And then you would do a proof. So the natural inclination, like in a mathematics class, like Cal State Fullerton, this is math 440 or something like that. You would learn to do a proof like this. So in order to show that conjunction is associative, this structure must be logically equivalent to this structure. And something that's quite popular is to do a reductio ad absurdum type argument, which is also known as indirect proof. Right? So you suppose one thing and you show that it leads to a contradiction, and so your supposition must be false. And that's all part of this efficiency. So Jeffrey wants you to really be thinking in terms of refutation and contradictions. And that's what he means by efficiency, is think about a counterexample. Where would we get a contradiction? And let's try to get to that contradiction or rule it out as a possibility as quickly as possible. But, and then also, his efficient method, like when he actually describes, when he gives his efficient proofs, they're kind of like schematic versions of this type of proof. So this is a more elaborate, formalized sort of proof procedure that's very popular in mathematics. But Jeffrey wants to just let's just call it a counterexample and let's just cut to the chase and let's just be a little more abbreviated and let the reader fill in the blanks. Let's not be overly explicit. So proof. Okay. So suppose that conjunction, that's the wedge symbol. So conjunction is, and Jeffrey describes this in chapter 1. There's a truth table for this, and is basically maps to the English usage of and. Okay. So let's suppose that conjunction is not associative. That, Matt, you've already shown that it is associative. So we're assuming something that we know to be false. And then we're going to show that gives a contradiction. And therefore, we know that the opposite of what we assumed is true, which is what we really wanted to prove. So this is a reductio ad absurdum. So you assume the opposite of what you want to prove, show that the assumption leads to a contradiction, and then you prove what you really want to prove.
Absurd.
Yes. So it's a little convoluted. And so, some logicians or even mathematicians, they don't like proofs by reductio because it's indirect. They would prefer a direct proof that goes step by step, like using the rules of inference and rules of equivalent, maybe not in detail like we do like in 1 of 6, but something that kind of has that feel to it without using indirect proof. But then in real life, mathematicians are always using reductio in their head because that's the efficient way to get to it. That's how they know the answer so quick. And they do it just kind of intuitively. They're not really thinking through all these steps explicitly. Their mind just captures it in this way. Okay, so let's suppose the opposite of what we want to prove, that conjunction is not associative. Then both A and B and C is not logically equivalent to A and both B and C. Okay. That means that there's a case where both A and B and C is true, while A and both B and C is false. We'll call this case 1. All right. So that's a possible counterexample, a potential counterexample. We'll call that case 1. Or there is a case where both the A and B and C is false, and A and both B and C is true, the other way around. The truth value is the other way around. We'll call that case 2. So case 1, suppose both A and B and C is true, and A and both B and C is false. Since both A and B and C is true, right? Since this is true, A and B must be true, and C must be true. So we're focusing on the dominant operation. The left-hand side has to be true, and the right-hand side has to be true. And so I'm just stating that explicitly. Since A and B is true, A and B both must be true. Then all 3 are true. A, B, and C, all 3 have to be true on our assumption, on our supposition of case 1. But this contradicts the supposition of case 1. So that supposition, this supposition must be false. And this is an indirect argument, or also known as reductio ad absurdum. So if we look on the student learning outcomes on the syllabus, this is one of the things that's mentioned there. And Jeffrey isn't really, he doesn't want to go to reductio or indirect proof because this is not very efficient.
Yeah.
Right, but it's more explicit. But then his efficient method is basically the same thing. It's just more sketchy.
Don't you have to have a case 3 where you suppose they're both false, or no? Because then that's associative, so it doesn't matter.
No, because if they're both false, that wouldn't be a counterexample.
Right. All right.
And then case 2, now let's suppose that the first one is false, second one is true, so the other way around. And so similar to case 1, the truth of A and both B and C entails that A, B, and C are all true, which in turn means that both A and B and C is true, contradicting the supposition of case 2. So it's basically the same thing all over again. And so, we say similar to case 1 or similarly, and that's a kind of convention. This is where you truncate things. It's basically just the same thing as case 1, just flipped around. Okay. So we've shown that our original supposition leads to a contradiction in every possible case 1 and case 2. So our original supposition is all the way back up here. That conjunction is not associative. We've shown that that's not a possibility. Because it leads to a contradiction in every possible case. Hence, the original supposition is false, again by indirect argumentation. Therefore, conjunction is associative, which is what we actually wanted to demonstrate. So that's what an indirect proof, sometimes referred to as reductio ad absurdum, reducing to absurdity or reducing to contradiction, right? That's sort of a more traditional approach. So the efficient way of doing this. And so the efficient method, I think one way of thinking about it is that it's like reductio. We're just like sketching what a reductio ad absurdum argument would look like. And so, but we want to focus on a counterexample. So a counterexample for associativity of conjunction would have both A and B and C true and A and both B and C false, or vice versa. Okay. suppose the first is true, then all three variables are true, making the second one true. So the first form of counterexample does not exist. Similarly, the vice versa form doesn't work out either. And you just let the reader fill in the blanks. You know, do all the thinking through that was made more explicit up here. So you see what I'm getting at?
Yep.
Okay, so that's kind of the general idea, right? So
Yeah.
but I got a little bit more explanation to do to kind of lock this in.
See, I didn't even realize that like counterexample and the method were like, they were so linked.
Yeah. And so that's, and that also now when we get into chapter 2 and chapter 3 and everything, you want to be thinking in these terms. The tree methodology is really looking for counterexamples. It's doing it in a mechanical way.
Yeah.
And so that's why, you know, Jeffrey could go into long explanations in chapter 1 about reductio and indirect proof and rules of inference and all this kind of stuff. But in chapter 2, he's going to blow that out of the water with a very simple mechanism.
Yeah.
And truth trees go way beyond what a truth table can do. But it's mechanical, just like a truth table. And what's the key to it is that it is about counterexamples, refutation, interpretations that might be counterexamples. And you know, from your experience with truth tables, you've kind of tried to do that by using truth tables, but it just doesn't quite. It's not as, you know, there's still a lot of opportunity to miss the counterexample, right? Because there's no really systematic way of just getting to it. The truth tree gets you to it. Or it shows that there is no counterexample. Okay.
Yeah.
And either way, that's great. And then Jeffrey just shows how we get tons of mileage out of this. Okay, so let's look at modus ponens. P only if Q, P therefore Q. Okay, this is a common argument form. We intuitively, you know, recognize this as a valid form of argument. You say, you know, if you eat too much candy, you're going to get sick. You've eaten too much candy, that's why you're sick. That's a conversation I have with my kid.
Modus ponens, Dad.
Okay, so yeah, modus ponens. I'll get her to recognize that in a couple of years. Yeah. So it's a valid form of argument. And we can put arguments in this vertical form like Jeffrey does in chapter 1, or we can do it horizontally like this. And this symbol is sometimes called a turnstile. It indicates the therefore part. Okay. And Jeffrey, of course, gives us this definition of validity. A valid argument is one whose conclusion is true in every case in which all of its premises are true. And a truth table explicitly describes all the cases. So as Jeffrey's discussed, if you have two variables, you have 4 rows. We use this pattern of trues and falses as a convention, and using the truth tables in chapter 1 for material consequence for a conditional statement, we get these values. P is just the values from the first column here. Q is just the values from the second column here. And then we see, okay, a valid argument is the one whose conclusion is true in every case in which all its premises are true. Okay, so each row is a case. In the first case or first row, all of the premises are true. And the conclusion is true, so that fits the definition. In case 2, not all the premises are true. Case 3, not all the premises are true. In case 4, not all the premises are true. So the only relevant case is case 1. And in that case where all the premises are true, the conclusion is true, it fits the definition of validity. Okay. Okay, so this is a valid form of argument. I have this example here. Let P equal an elephant is a mammal, Q a whale is a mammal. If an elephant is a mammal, then a whale is a mammal. An elephant is a mammal, therefore a whale is a mammal. All right. This is a valid argument because it follows the modus ponens form, and it's actually also what? It's also sound because
it's true in reality.
And what is true in reality?
The statements, the premises.
The premises are true, and it's a valid form of argument.
Therefore,
we're guaranteed that the conclusion is true.
In reality.
This is a sound argument. Okay. But now let's let P equal a hare is a mammal. Is that true?
It is.
That is true. And Q, a tortoise is a mammal.
That is not true.
That is not true. But if we put it into modus ponens form, it is a valid argument if we say if a
no, rewrite it.
If a hare is a mammal, then a tortoise is a mammal. I must have changed this at some point. A hare is a mammal, therefore a tortoise is a mammal. Okay. So this is an unsound argument because the first premise is not true. The second premise is true. But the first premise isn't true, so that makes it unsound. Okay. Let's try another example. If you stand a little to the left, you can see the departure schedule. You do stand a little to the left, therefore you can see the departure schedule. Okay. This is a valid argument. We'll also assume that it is sound. But there is a form of argument that looks very similar to modus ponens, but is actually not valid. And you talked about this in your presentation, right? So denying the antecedent. What if you refuse to stand a little to the left? We might be inclined to believe that you can't see the departure schedule. If you stand a little to the left, then you can see the departure schedule. You don't stand a little to the left, therefore you can't see the departure schedule. This, however, is an invalid form of argument. So it's neither valid nor sound. Even if we assume that the other version, the modus ponens version, was sound. Now it's called denying the antecedent because the antecedent, a conditional statement using material consequence, using the arrow, has two parts. The antecedent, which comes before, and the consequent, which comes after. Okay, if we deny the antecedent in our second premise, we get this form. All right. So in modus ponens, we had no negation here. So we're putting a negation in there, and then sometimes we're inclined to think, oh, then Q must be negated. But if we look here, we're looking for rows in which all the premises are true. And in the third case, all the premises are true, but the conclusion is false. So this is an invalid argument. And all we need is this one example, this one counter example. All right, so this is a counter example where P is false and Q is true. That's a logical possibility. And if we want to show efficiently that denying the antecedent is an invalid form of argument, we need to home in on that counterexample. That's what Jeffrey means by efficient. Let's just cut to the chase. Let's cut to the counterexample. So how do we get there as quickly as possible? Okay, so for example, in terms of trying to see the departure schedule, it could be that you take 2 paces forward, and if you do so, you can see the schedule, right? We can imagine such an arrangement. You, in fact, don't move a little to the left, so we deny the antecedent. Nonetheless, you get to a position where you can see the schedule. And so the consequent is true. So this kind of denying the antecedent is a kind of fallacy called overlooking logical possibilities. Okay. And namely, you're overlooking the counterexample. Okay. So we can do this efficiently. And so we can prove that denying the antecedent is invalid with an efficient proof that looks like this. A counterexample to the validity of the argument would have not P as true and Q as false. That means that P would be false, right? If not P is true, then P is the opposite, P is false. And since not Q is false, Q also would be true. Both are true. And if we look at the lookup table in chapter 1 for the definition of material consequence, we see that this will be true. So counterexample exists where, and I'll use this sort of notation. I don't think Jeffrey does this, but I do this. These are ordered pairs. So P comes first, Q comes second, false comes first, and true comes second. So they match up. P is false and Q is true. So those are like ordered pairs like X and Y on a Cartesian coordinate system, X and Y. All right, so then back to modus ponens. Now, focusing on the potential existence of a counterexample, the potential existence of a counterexample. We know that there is no counterexample to modus ponens, but we're going to focus on the possibility that there might be a counterexample. And that gets us to an efficient proof. So this is it right here. A counterexample to modus ponens would have P is true and Q is false, right? The second premise would be true, but the conclusion would be false. And the counterexample would also have to have P only of Q being true. But if P is true and Q is false, that's precisely the case in which P only of Q is false in the truth table in chapter 1. So no counterexample exists. Done. you see why we call this the efficient method. Arthur, are you following along with this? A little bit. I mean, I know you just walked in, so.
It's all being recorded. You can watch it in the video.
Yeah, but so we're trying to figure out what Jeffrey means by the efficient method of proof. And it all comes down to focusing on the potential existence of a counterexample. You either want to show that there is such a counterexample or that it's not possible for such a thing to exist. And that gets us to where we want to be. Okay, any questions at this point?
Much better now.
You're much better now. Okay. Now there are some problems that come up in the problems for chapter 1 in section 1.18. There's quite a number of problems where we're talking about logical equivalence. And so I just want to translate what I just did into a situation where we have logical equivalence. I want to explain kind of in terms of what I've said already, what logical equivalence is here. So you can have a one premise argument. You can have an argument with just one premise, P and Q. This is the turnstile, means therefore, and then the conclusion. So both P and Q are true, therefore P is true. Does that sound reasonable? Both P and Q are true, therefore P is true. Okay. And if we put it in a truth table, we see, in every case where all the premises, all one premise is true, the conclusion is true. There's only one case in which all the premises are true, and so it's a valid form, according to the truth table sort of way of looking at it. We could do an efficient proof. The counterexample would have P is false, but then P and Q would be false, right? A counterexample would have to have P false, right? You have to have whatever the conclusion is, it has to be false, and the premise has to be true. And so if we assume the conclusion is false, well, then the premise is true, is false. Right? Because if either P or Q is not true, then P and Q is false. So no counterexample. And this all just comes from the definition of validity. Okay, now logical equivalence. Two statements are logically equivalent if the one premise argument from the one to the other is valid, and the argument from the other one to the first one is also a valid inference. It goes both directions. So here we're going to start with, so I'm going to use some different statements here. So we're going to treat this as the premise, and this is the conclusion. And in case 1, 3, and 4, where the premise is true, the conclusion is also true. So that's a valid inference going from this premise to this conclusion. Okay. Now let's do it the other way. Let's take this as the premise, right? So what was the conclusion now is the premise, and it works out the same. All right, so it works out either way, right? We're going one direction and then the other direction. So the truth tables show that these two are logically equivalent, and we can symbolize it with this symbol. So this 3-bar symbol is often used to denote logical equivalence. And so we could just put it all into one truth table that looks like this. But we have to think about it going both directions. We have to think, oh, this is the premise going one direction, and this is the premise going the other direction. And you got to check it. But basically, it comes down to that they have to match. When one is true, the other is true. When one is false, the other is false. So as long as they match, then they're logically equivalent. Okay, any questions about that? You with me? Okay, good. All right, so then this comes up like in problem 17. Because the definition of associativity is really a definition that involves logical equivalence, right? And so a counterexample in kind of truth table form, we don't know what A and B would be here, right? But assuming that there is a counterexample, hypothetically, it would have to have this structure: true, false, or false, true. They would just not match. So we have two potential counterexample cases. One where, however we would say that in English, where this form is true and this form is false, and then the other way around. So efficient proof for conjunction is associative. I've already done up above, but I think this is worded a little differently. So let's read through it. So a counterexample would have both A and B and C as true and A and both B and C false, or vice versa. Suppose that both A and B and C is true, then all three variables are true, making A and both B and C true, when it would need to be false if we're going to be a counterexample. Likewise, if we suppose A and both B and C true, then both A and B true and C true is true. Thus, we have no counterexamples, because whenever we assume one is true, the other has to be true. So conjunction is associative. All right, so that's worded a little differently from what I had up above. The efficient proof for associativity of disjunction. So we want to prove that, right? The truth table definition of disjunction is a little different from conjunction, but the proof is going to be very similar. So it's going to look very similar to this. So that's something you might want to do, right? Let's try to do an efficient proof for disjunction, following the model. And I have, two different versions here. So, you can word things differently.